Let's take a look at another application word problem using calculus. Jimmy picks up a soccer ball and kicks it up into the air. The height of the ball in meters is modeled by the function h at t equals negative 4.9 t squared plus 15t plus 1, where t is the time in seconds after the ball is kicked. Part A. What was the maximum height of the ball, and at what time was it reached? Okay. How do we find the maximum height? Well, just like our last question we did, if I do a very crude drawing here of what our graph looks like, our height graph, we can take a look and say, okay, well, it's a negative quadratic, so it opens downward. It has a y-intercept of 1, or an h-intercept of 1 in this case, which means it looks something like this, where this is your time in seconds, and this is your height in meters. We're looking for this point here. That's what we're interested in finding, right? We want to find the time when it hits that maximum, and we want to figure out what that maximum is, that height right there. So how can we figure this out? Well, in the past, we would have solved this by figuring out where the vertex is, right, of the quadratic. But we want to practice using derivatives because in the future, you're going to have questions where they're not all quadratics, right? They can be more complex looking equations. They can be trig equations. They can be higher degree polynomials, all sorts of things. So we want to practice using this method. Now at that point, if we draw a tangent line, the slope of that tangent line would be 0, right? The slope of the tangent at the maximum is 0. So what we want to figure out is where's the derivative of this equation equal to 0. So let's take the derivative of that equation, h prime at t. If we do this, we're going to get negative 9.8t plus 15. I'm just using the power rule to take the derivative of this. Now we want to figure out where this is equal to 0, so we can say 0 is equal to negative 9.8t plus 15, and now we can solve for t. 9.8t is equal to 15. I'm just doing the algebra. So t is equal to 15 divided by 9.8. And if you do that, you should get 1.53 seconds. I rounded that answer off to a couple decimals, but it's actually a longer decimal than that. So 1.53 seconds approximately is where this maximum is taking place. And you could have also solved that using, like I said before, various methods for quadratics, right? You could have used the x is equal to negative b over 2a, if you remember that one. That will give you the same answer here, 1.53, but we want to practice using derivatives instead. Okay, so now we want to figure out what is the maximum height at that point in time. Well, all we have to do is plug in that value, 1.53, into our original equation for height. And if we do that, we'll get negative 4.9 times 1.53 squared plus 15 times 1.53 plus 1. And if you do all that math, you should get a value of about 12.5. I'm rounding that to one decimal place, and the unit is going to be in meters. So that's the maximum height the ball achieves, and it happens at 1.53 seconds. So that's a pretty good kick that this guy got on the ball, because that's a very high distance off the ground. Okay, let's look at part B. Part B says, how fast is the ball moving vertically 2 seconds after it was kicked? Now this is important, right? The height equation we got, that's a distance that is only vertical. So if we take the derivative of that height equation, if we find h prime at t, that will give us the velocity equation, but that velocity is only in regards to vertical height, right? It's not actually tracking the distance the ball is going, right? Like if the ball gets kicked and it goes like this, it's not measuring that distance along that curve. It's only measuring or showing us the height changing as the ball moves. So that's what they're asking for, right? How fast is the ball moving vertically? So just that vertical speed. Okay, we already did this, right? We got the answer negative 9.8 t plus 15. Okay, so we want to figure out how fast is the ball moving 2 seconds after it was kicked. So we want to find v at 2. If we do v at 2, we get negative 9.8 times 2 plus 15. And if we do this math, we should get negative 4.6 meters per second. When you get negative, that just indicates the direction. So another way to say this would be 4.6 meters per second downward. So you can provide your answer like that as well. If we're thinking of what this graph looks like again, where this is your height changing over time, right? This h-axis is your height, but this axis on the bottom, that's not your horizontal distance, right? That's the time. For all we know, the ball is actually traveling like this, or the ball could be traveling like straight up in the air and back down. We don't actually know because we're not given those horizontal measurements. This x-axis is just your time, okay? Now, at 1.53 seconds, we know we're at the maximum, and we found the tangent line there, or we said that the tangent line there had a slope of 0. That actually means your velocity is 0, which makes sense because when you kick it, you can see the rate of change changing, right? Like if you make a tangent line here, it's pretty steep. When you get to here, it's a little bit less steep. The ball is slowing down. And then when you get to here, it's at 0, right? Now when the ball starts coming down again, it starts getting steeper until you get to down here. It gets even more steep than that, right? The tangent lines get steeper around these areas, and as you get closer to that center, the tangent line is very flat. So actually you kick the ball, it's going very fast, and as it goes up in the air, it slows down, it stops for a moment, and then it comes down and it starts speeding up as it falls, right? So if you're thinking of the point that's at 2 seconds, you're thinking of this area here. If you find the slope, you'll recognize that it's negative, right? Because it's going downward. That's why we got a negative 4.6 meters per second. And of course, the units are in meters per second because the height is in meters. The time is in seconds. If you find that rate of change, it's rise over run. Well, the rise is in meters because it's along that h-axis, and the run is in seconds. So if you find that slope, rise over run, meters divide by seconds, you get meters per second. So hopefully that makes sense. Okay, let's take a look at part C. What is the ball's vertical acceleration right before it strikes the ground? Okay, so the acceleration graph, to find that, all we have to do is take the derivative of v at t. So to go from the height graph or the height equation to the velocity equation, we took the derivative. To go from the velocity equation to the acceleration equation, we take the derivative again. So just to remind you, the v at t was equal to negative 9.8 t plus 15. If I take the derivative of that down here, you're going to get negative 9.8, and that's it. Okay? Now, there's no variables here, so we don't have to figure out what the time is when it hits the ground to plug in here, because no matter what value we plug in for t, you're going to get the same answer, negative 9.8. More specifically, you could say 9.8 meters per second squared downward. Or you could draw an arrow going down if you wanted to. Now, this is significant because 9.8 meters per second squared, and to be more precise, 9.81 meters per second squared is actually what we consider to be the acceleration due to gravity on Earth. So if you ever drop an object or you see an object in free fall falling towards the Earth, it's always accelerating at a rate of 9.81 meters per second squared. That's the value you use if you take a physics class at this level. That's what you're always using for your acceleration due to gravity. So that's a constant value. So it makes sense that when we took the derivative of this, that's what we got. And if you're wondering, well, how could that happen? It's because I didn't make up the original equation. Well, I did, but I made it specifically so that this would be the acceleration, because that's the only acceleration really possible in these types of questions.